Good morning. Welcome to Krishna's classroom. Right, it is afternoon. Yeah. We were looking at the pointwise convergence of the Fourier series on CT. But we found that when we write down the Fourier series, generally we talk about what are called L2 convergence. And one of the questions that automatically comes up is, suppose you take the Fourier series, is it pointwise convergent? Which means if the function f is the one for which the Fourier series has been written, then you are asking the following question. That means if f is a function for which Fourier series is written, okay, then of course what happens is Cn turns out to be this is the Fourier series that you have. Then you know that this converges in the following sense, that f minus Sn that in the L2 norm this converges to 0 as n tends to. And we also know how Cn looks like. Cn turns out to be inner product of but this is the coefficient which is also often designated by f as the transform. This is the transform condition. Now the problem that you have listed last time is this. Now we are taking f to be in C. For details, you check the last lecture. Now you see the problem that you have is these are continuous functions on the unit circle, and or in other words, these are the periodic functions with period 2 pi defined, periodic continuous functions defined on the interval on R with period 2 pi. Okay, so f is periodic. With period 2 pi on R, this continues. And that is what we denoted by CT. All continuous functions, continuous, complex valued, periodic functions on the interval minus pi to pi, or on R, which is with period 2 pi. This is what we have looked at, and these are the functions CT. And for CT, you see all this is well defined. and this integral exists, etc. So CNs are well computed, therefore the Fourier series makes sense from that. Now the question that you ask is this: for any x fine, or for any x belonging to R is limit v equal to that means whether at each point the partial sums of the series converges to the functions. Actually, let me just digress a bit and say few words about convergence of the series. Now, this is because somebody raised a question last time. There was an email. Oh, sorry, there was a note at the end of the lecture, and he wanted some explanation for what we mean by convergence. Suppose you take R, and on R we have dxy defined as x minus y. Now, this is a metric, or what you call a distance function. Satisfies all the basic requirements of being a distance function. All the basic qualities of the distance is satisfied by this function. Now, what you have is this. Suppose you have a sequence. Xn belongs to R. Okay. This is a sequence n running from 1 to. Question that you ask is, what do we if at all there is such an x exists? It may exist or may not exist. For instance, you take the sequence example. Now you see you have the sequence 1 by n, and in this case x is equal to 0. Makes sense. As n tends to infinity, it goes to 0. Now, that is the first one. 2. Example 1. That means all elements are, or I will put it this way. Then you see that x this sequence, the limit n tending to infinity equal to infinity. That means this sequence does not converge. Now, third example is you look at the sequence 1 minus 1, 1 minus 1, 1 minus 1, etc. Now, this sequence, so xn is equal to minus 1 whenever n is even, equal to 1 whenever n is odd. This is the sequence that you have. Now you see that this sequence neither converges to 1 nor converges to minus 1 nor to any other. So this sequence is not convergent at all. Now the second sequence we can say at least it diverges. This one doesn't converge at all. Say that so what do we mean by convergence? The convergence means this is a sequence x if the following is true. That is equal to 0. Equal to 0. This means, in a more refined language, this given epsilon positive, where x is n, such that mod xn minus is less than epsilon for every n greater than n, and this n depends on epsilon. So for each epsilon there should be a corresponding n such that this property is. Okay, what does this mean? I mean, this was quite easy to see. What happens in the first case, you see that 1 by n converges to 0. So if you try to understand this, this is 0, this is 1, this is half, this is 1/4, sorry, this is 1/3, this is 1/4, etc. As you see that as n tends to infinity, it keeps coming closer and closer to this. So you choose an epsilon neighborhood of 0 to see that from some stage onwards, all the elements of the sequence happen to be in this way. Now this is what we mean by it, or in some way to say that the terms are trapped in a neighborhood of 0. Okay, so you take any neighborhood of 0, there is a corresponding n such that for all n small n greater than capital N, this is true. When I am talking about this is the statement, the refined statement of the convergence. Look at this, whether this happens or not. So for no n, see that if you plot these points, now you see that this is 0, 1, 2, 3, etc. This is the sequence. So n plus. Okay. Now you see that there is no such n, real number n, such that if you take a neighborhood of that, should contain the complete tail of the sequence. This is not possible. Therefore, it does not converge to any point here. In other words, but you see that this is limit n tends to infinity, xn goes to infinity. Okay. Therefore, we say that the series diverges. Okay. Right. Now the third example, 1 minus 1, 1 minus 1, etc. Now you see that in this case, if you take the sequence 1 minus 1, 1 minus 1, etc. So xn is equal to, whenever n is odd, equal to minus 1. Now you see that the 2 points where it is likely to converge are minus 1 and plus 1. This is all that we need to investigate, because if you take this is 0, minus 1, this is plus 1. Now if you take any other point, say either here or here, which is not equal to minus 1 or 1, including 0, you can always find a neighborhood of that point which does not contain either minus 1 or plus 1. This is always possible as long as that point is not equal to plus 1 or minus 1. Okay. So we can immediately conclude that the convergence criteria fails to hold if you choose the point as anything other than minus 1 and plus 1. So now what you have to investigate is this, whether it could be plus 1 or minus 1. Suppose you take plus 1 and then choose a neighbor. You can always find a neighborhood such that the sequence, around 1, if you are taking the neighborhood around 1, then you see that only xn when n is odd is in this neighborhood, and xn when n is even, it is not in the neighborhood. Therefore, our criteria that the tail of the sequence, that is from some stage onwards, xn onwards, all the elements are in the neighborhood, is not valid. Okay. So we say that this sequence does not converge to any point what you call an oscillator. Okay. Now there are a lot of examples that you can make, or this itself can be written in the form minus 1 to the power n plus 1. This is the sequence. When n is odd, it is equal to 1, and when n is odd, well, this is the sequence. Okay. Now you need this information to work with a series. What is a series? A series is something else. Now remember, in a metric space you cannot talk about a series, because it does not make any sense to talk about summing up to adding two elements of the metric space. It may not make any sense. Okay. So in a general what you call metric space, This does not make any sense. But then in any linear space, it does make sense. You can talk about n equal to minus infinity to plus infinity. This is possible. Or n equal to 1 to infinity. All this is possible. Okay. All this makes sense if you are in a normed linear space. Okay. So let me come to that. Let us confine ourselves to the real line, which is the model that we pick up. And then you see that if you look at this, how to give a meaning to this? How to attribute a meaning minus infinity to plus infinity an or okay. Here is what you do, because we know that for a sequence you can attribute a meaning, and you have the notion of convergence. Therefore, the problem is to approach this through the sequence route. What is it? Now let us write down. See, in this case we write Sn to be equal to sigma minus n to plus n at. Okay. Then what happens is you have a sequence Sn. Now this has been constructed out of the given series. Okay, and formally okay, so what you are doing, this is Sn. Sn tends to infinity, you change n to minus infinity and plus infinity. So limit n tending to infinity Sn. Now it makes sense because we already know. So from the series we have constructed a sequence. Okay, so that the limit of the sequence becomes essentially the sum of the series. Form. Okay, therefore now you can talk about the series, the infinite series. So we say that sigma n equal to minus infinity plus infinity an converges if the corresponding sequence Sn converges. Okay, so we shall write so from the sequence you construct from the series you construct a sequence, and such that formally, so from the series construct a sequence formally the limit of the sequence is the series, as we have seen. Okay, so you have, this is what you have. Okay, therefore, now we know a lot about the limit of the sequence, and you can apply every bit of that and talk about the convergence of the series. Now, this is the whole idea of talking about the convergence of a series. And in the second case, this would be, see, the partial sums would be 1 to n ek. This is Sn, so limit n tending to infinity Sn equal to given series for value. This is for value. So you ask whether the sequence converges. If the sequence converges, then the limit of the sequence is the series that is the whole idea. Okay, so what you do is from the series you construct sequence and then look at the limit of this, and once the limit exists, then you say the series converges. Otherwise, you say the series diverges or series oscillates. Depends on what type of terms that you have. Now you see, this whole idea can be pushed across for in any normed linear spaces. In the normed linear spaces, you have what are the facilities that you need? You should have the sum of two vectors defined. That is there in a vector space. Okay. Therefore, sum of n vectors is defined for n any large number. So all finite sums are defined. Therefore, given a series, it makes sense. Okay. So suppose you take the same series. Now these are elements of a normed linear space. Then this makes the partial sums do make sense. And the partial sums do make sense. That means each Sn makes sense because it's a finite sum, and you are in a vector space. Therefore, this makes sense. Okay. Now the question that you ask is this: you have the concept of a norm. Norm is a distance function that you have defined in the linear space. So, in terms of that, can you talk about the convergence of the sequence? Just word by word, write everything. Instead of modulus, you write mod x is to be replaced by No. This is the only thing. So this is exactly what we are trying to do. Okay. Now the present problem. Now we can come back to our problem. Our problem is what? We are going back to this. Okay. So let me just work it out. So for each x, what you have is this. So for each x, Cn for the Fourier series is a function of is a number which depends on the particular x that you are choosing. Okay. Now we are interested at each point. This is what you mean by pointwise convergence. So the question that you ask is the sequence Snx to f of x, because this series can be constructed from f. Okay. So this is related to, okay, this is related to, so what you have is this f. This is the Fourier series. So what we are asking is, for each x, does the partial sums or do the partial sums converge to the value of the function at x? Okay. So for each x, this is the meaning of this. Okay. And this problem is, once again, once you fix your x, what happens is, this Snx is a sequence of numbers. Okay. And then that makes sense. See, so you are talking about a sequence of points on the number line, and you are asking whether that sequence of points do converge or not. This is the question that you are asking. Okay. And now let us come back to our notations. So we have, see, we have the following for f belonging to Ct, we have Sn equal to sigma minus n2 plus n This is what you have the sequence. For each x, this of course becomes a number. No? And you are asking about the convergence of this sequence. Therefore, you have a sequence the sequence that's it. Okay. Now f is taken as an element of you know that this question should pose in L2T, does not make any sense. This pointwise convergence is not assured by convergence in the DOM. Okay, so it is not there, but for continuous functions, at least we expect this result to be true, and quite a reasonable question that one can pose. Okay, so let us work on that. Now we know that for every CT is contained in L2T, and hence this is what you have. Goes to 0. This is the L2 now. This is the L2. Okay, so it's on the average you want this to go 0, but that is not the problem. What we want, what you have now is this, a more deeper question. That is, this sequence, these are sequence of functions now, converges in L2 T to F this is what we infer from it. But our question is talking about it for each x whether this converges or not. So let us explore that. So what you can, so we are taking CT to be a part of okay. Now what you can say is at the outset is that so one cannot say that Sn one cannot say that converges pointwise on as a consequence of L2 convergence. This means if Fn converges to, if Snfx converges to F in the L2 now, does not mean that it converges the sequence, at least left to this one. UN confined to CT converges to this one. So what we can say is that there exists a subsequence of SNFX which converges to but this is not something that we are after. What we are asking for is does the partial sums converge to the value of the function at each point x. Okay. So this is the question that you are asking. Let us see how we can go about investigating. Now, while investigating this, we make use of the Banach's type procedure. We make use of so let us write down the statement of it. Make some notations. We put we denote this by we take good 0. So we define the following. Now define zero. This is for n equal to 0, 1, 2. Designated, right? So we are trying to find out whether this goes to a. Is there any chance that if this sequence would converge to a finite? So let us work out this. The appropriate theorem is that something that talks about transformation. I mean, these are linear maps. Okay. So we'll write down the DS theorem. Let X be a Banach space and Y a non-linear space. It's a non-linear space. Let lambda alpha be a collection of bounded linear transformations bounded linear transformations of Y. Then two things can happen. Either there exists in M finite such that is less than 1. That means all the lambda alphas are uniformly bounded on CT. So this is the bound for the operators. Okay. For every alpha belonging to the index set. So A is an index set. They not say that. So this is an index set. A is an index set. For every alpha belonging to A. Or the other possibility is that supremum of A These are the two possibilities. Now, this is the Banach-Steinhaus theorem. For every x belonging to some dense G delta what exactly we mean by G delta? G delta is, see, G is coming from the German word geöffnet. That means open. Okay? And delta comes from the word that it is Durchschnitt. That means intersection. So this is actually a set, a particular set is said to be a G delta if it is the countable intersection of open sets. The finite intersection of open sets is open, but we cannot make that statement about countable intersection of open sets or arbitrary intersection of open sets. We cannot make that statement. Whereas countable union of, or for that matter, arbitrary union of open sets is open. So this is actually the countable or arbitrary union intersection rather than open sets. Intersection of open sets you are talking, which may not be an open set. This may not be an open set. Okay, right. So such sets are called G delta sets. Similarly, you have what are called the F sigmas, the countable union of closed sets. Okay. Now, what we have is this. So that's the statement of. We'll apply this. Now, CT is a Banach space. It's a Banach space relative to the soup law. This is what it's called, the soup law. But pointwise limit is a different thing. Okay, supremum norm is something, but pointwise, see, supremum norm is this. X belonging to T whatever. This is the soup law. Okay, because this is a periodic function, and on interval minus pi to plus pi, that is the relevant interval, on this function is a continuous function, therefore it is bounded. And therefore, on the compact interval minus pi to plus pi, this is a bounded function, therefore this exists. And this is what you call the soup norm. Okay, and with respect to the soup norm, CT is a Banach space. Now we have Sn defined as 1 by 2 pi. This we have proved already. This is the designate one. We have used it earlier, where this we have proved last time. This is equal to this is the edge. So this we designate by 2. Okay, and that we have proved last time, right? So lambda n is a bounded linear function it's a bounded linear functional on CT. Look at the definition of lambda n. How have we defined this? You have defined this as lambda n equal to lambda n equal to 1 by 2 pi equal to minus 0, minus t, and this is cos. Okay, this is what you have as lambda nf. Therefore, you can calculate this. And immediately see that norm of lambda n is less than or equal to 1 by 2 pi because we are taking supremum over all f norm x equal to 1. Therefore, this estimate is there, and therefore this is equal to this is real. Okay. Therefore, we claim that infinity as an infinity. Okay, I think this is a place where we can stop today, and maybe we will take it up tomorrow to continue with it, or at a later convenient date. Okay, so thank you very much.